Everyone, well, first I would like to thank the organizer for organizing this event and for inviting me, and also in Moscow. So, in fact, on the program, I gave two different titles. So, so in the long version of the program, it's called Statistical Physics on a Random Lattice and Conformal Field Theory and Integrability. But in the other version, it's also written Random Matrix Methods. While this conference is mostly about conformal field theory and integrability, so I will give an example of a problem where we have conformal field theory and integrability, which comes from statistical physics on a random lattice. In fact, I will probably not talk too much about random matrices, although all this was first inspired by random matrix techniques. But now we have found a way to completely eliminate the notion of random matrix from the presentation. I mean, it was just random matrices were more like a notation, a convenient notation, but you can just forget about it. In fact, there is another thing which will invite itself in this problem. It's geometry, exactly like in Professor Tartajan's talk. It was supposed to be about Liouville theory, but you see that geometry plays a very important role, and so there is also geometry. And in fact, it will be algebraic geometry mostly, which will play a very important role, but which is very deeply connected to integrability, and as we have seen before, to the notion of conformal field theory. So let me present the problem which we want to consider. We have, so what is a random lattice? A random lattice, let's say, typically it will be, let's say, a triangular lattice. In fact, two-dimensional. So it will be triangles. A triangulation of a certain surface. So basically, it's a graph made of triangles drawn on a surface, and very often people call it map. Well, it's called map because imagine, for instance, the triangles are somehow the countries, and the surface is the world. So it's a map of the world where there are countries. So and the surface can have an arbitrary genus. So it's more or less a graph on a surface. In fact, it's the equivalence class of graphs modulo isomorphisms of graphs on the surface. So a map is really basically it's a graph embedded into a surface up to reparametrization of a surface on the graph, more or less. Well, I don't want to enter the precise definition. So we have a triangulation of a surface, more or less. We can do the same thing with quadrangles, with other polygons. We can consider other polygons like quadrangles, like diangles. And some of the faces also will be marked faces. And each time we will have a marked face, we'll also mark an edge on the marked face. And okay, we have a triangulation, okay, covering the surface. There will be extension of that problem where we can also consider some structure on the triangles. For instance, the triangles, so generalization. Typically, it will be colored faces. So for instance, triangles can carry a color. Let's say, imagine there are two possible colors, let's say black and white, or let's say plus or minus, plus, minus, plus, plus, minus, minus, plus. Okay, in all possible ways. And this will be a kind of Ising model. On a random lattice. So we'll consider the set of all possible maps and put a probability weight on it and try to see what happens when we consider maps with a very large number of triangles, a very large number of pieces. And the guess made by physicists, but which is not yet proved, unfortunately. So the guess is that the limit of such random maps with possibly an Ising model on it or another statistical physics model on it, the limit of very large random maps should be the Liouville conformal field theory. So the same Professor Tartajan is talking about. So this is the guess. This is not proved. But we can prove a few, we can prove a few identities which confirm this guess. And this is what I would like to talk about. So, I first have to define which probability measure I will take on that. Okay, I will say it in a minute. So which weight I give to each map. So the conjecture large maps converge to Liouville and possibly Liouville coupled to what's called matter. But this is mostly unproved. And so our purpose here will be much simpler. We will just try to basically compute the partition function, so more or less just the number of such configurations. We are just going to count the number of configurations. And well, the limit of the number of configurations can be computed in the Liouville conformal field theory, and basically we want to see if it matches. So let me be a little bit more precise now. So we are going to counting maps. So let me consider first let's say planar routed maps. So a planar routed map, well, maybe I should not say routed, but what I will call a planar routed map is a map where I have one marked face with one marked edge. So and it will be planar. So on the sphere, on the sphere, I have somewhere a marked face with a marked edge, and well, I'm only considering oriented surfaces. Well, here is the sphere. The sphere is oriented, so there is an orientation, and so the orientation of the marked edge is according to the orientation of the surface. So let's say, for instance, that the marked face is on the right of the marked edge. So and we have a triangulation. Which covers the sphere. Okay. And so on. Yes, so this is what I'm going to count. Every face except this marked face are triangles. In the end, I will be interested to count the case where even the marked face is also a triangle. But in order to get recursion equation, I need to consider at least one face which is not necessarily a triangle. So it's in order to get a recursion equation. So there is another thing I didn't say. So so I was not very precise in the definition of maps. So a graph is really a set of incidence relations. So which face is glued to which face along which edge. That's the set of incidence relation. But in the definition of map, in fact, you can glue an edge of a face to an edge of the same face. So there is this subtlety. We shall see it in a moment. So it means there can be some things quite singular, like sorry. Well, it's difficult to do with triangulations. Okay, well, okay, we will see an example later. So, so now I'm going to define a generating function. Which count those objects. So let me call it W1, 0. So the 0 here refers to genus 0. So it's planar. And the 1 refers to the number of marked faces. So later I will define WNG, where there will be n marked faces, and it will be on the surface of genus G. So it's going to be the sum over all maps with, let's say, t to the number of vertices. So vertices are those points. Okay, t to the number of vertices. Another coefficient, let me call it t3 to the number of triangles. T4 to the number of quadrangles. And so on, let's say TD to the number of d-angles. And another variable which I will call x to the number L, and L is the size of a marked face. So let's say this is L. L is the number of sides of the marked face. So, well, so I have a weight per triangle, a weight per quadrangle, a weight per d-angle. So here in this picture I put only triangles. In fact, in most examples later I will consider more quadrangulations. But you see, if you put T4 equals 0, T5 equals 0, and so on, you are counting only triangulations. So, but we will do the general case. So this is a generating function. So it depends on some formal parameters, x, t, t3, t4, and so on, td. Okay, I will always assume that unmarked faces have between 3 and d sides, and marked faces I will assume that L is simply larger than 1. So the marked face can have only one side. It's again because I want to write a recursion, and I can, it's easier to start the recursion at 1 instead of at 3. So, let's say.
Could you tell again what is x and what is t?
They are just formal parameters. So basically, x is a weight you put to each. So for each edge here, you put a weight x. So it's just a weight per edge of the marked face. And t is a weight per vertex. T3 is a weight per triangle. T4 is a weight per quadrangle, and so on. It's usually physicists call that Boltzmann weight. So T3, T4, and so on are Boltzmann weights. Well, and X and T also. So they are just formal parameters, which, well, either you say they are formal parameters which just allow to define a generating function, a generating series. Sorry, it's not a generating function, it's a generating series. It's a formal series. Or you can say this is a probability measure you put on each map. I mean, the weight of each map is t to the number of its vertices, t3 to the number of its triangles, and so on. So this is the probability measure we consider on the set of discrete maps. And the question is, does this probability measure converges to something interesting when for very large maps? And the expected answer is yes, but it should be the Liouville contourment field theory. Excuse me?
What's L?
L is the number of edges of the marked face.
Number of edges of the marked face.
It's the size of the marked face. And here there is an L plus 1. You will see why later, but it's because it's because of the geometry. There is a geometrical interpretation. So so we define this function somehow. It is a weight for so it's the sum of maps and a weight per map. For instance, imagine the expectation. Imagine you want to compute the expectation value of the number of vertices. Well, you just take d over dt, because you see that if you take a d over dt, that puts the number of vertices down. So it's d over dt of log of w10, and td over dt, this is the expectation value of the number of vertices. So it's just to show you that this function allows to compute expectation value of everything. If you want to know how many maps you have with a given number of triangles or a given number of vertices, you just pick the coefficient of, let's say, imagine you want to count how many maps you have with, let's say, 5 triangles. You just pick the coefficient of t3 to the 5. And that gives you the number of maps with 5 triangles. Okay? So this generating function, this series encodes the number of maps with given number of triangles, given size of the marked face. Right?
Where is the coefficient? All the coefficients are 1 in your formula.
Sorry, what do you mean? Yes, every map, so there is 1 per map times this weight. Okay, it's because we have, since we have a marked edge, there is no automorphisms of maps. So maps have no non-trivial automorphisms. So each map is counted with a symmetry factor 1. Right, so this is what we want to compute. And in the 60s, so Tutt, in the 60s, he found the answer to that problem. So he was able to recompute this series, which turns out to be a function, an algebraic function. So he computed it explicitly. So it's based on some recursion on the number of edges. So the idea is the following. Take a map and remove a marked edge, and basically you're going to get another map. Well, first, since we are on the sphere and we have marked face, we can always assume that the point at infinity is on the marked face. So it's better, in fact, to represent it this way. So the marked face now will be on the exterior, and the triangulation is in the interior. Something like that. So, and the marked edge is, let's say, here. So, and we have L plus 1, so, sorry, we have L edges. So L edges on the exterior. Well, let me define TL 0 to be the same thing here as here, sum of maps, but such that, side of the marked face so it's the same as before, t to the number of vertices, t3 to the number of triangles. Okay, so it's the same, but now I fix the size of a marked face to be exactly L. So basically TL0 is the coefficient of 1 over x to the L plus 1 in this series. So you can say that this is the residue of W1 0 times x to the L. So, because when you multiply by x to the L, the residue is the coefficient of 1 over x, so that's exactly what you're doing. Or if you want, the coefficient of 1 over x in this product is exactly the term with 1 over x to the L plus 1 in W1 0. So now, imagine we remove the marked edge. We get another map. Wow. Okay. We get another map, and now let's say well, the marked edge was there, so now let's say we mark this edge now. So we get a new map, and the size of the external face now is L plus 1. But this is not the only possibility. Another possibility could occur is that on the other side of the marked edge, in fact, there is not necessarily a triangle. There is not necessarily an unmarked face. On the other side of the marked edge, there could be the same marked face. So when you go across that, in fact, somehow this could be the same marked face again. So this is the case where we have, so on the sphere, so imagine we are on the sphere. Well, we have something like that. So the marked face is the face on the exterior on the sphere. It has side L plus 1, L. But when we remove the marked edge, we don't get, in fact, a map. We get two maps. Okay. So we get two maps, and now let's say we are going to mark this edge and that edge, so the ones which are adjacent to the marked edge, right? And that allows to write an well. So basically, so starting from this configuration, when we remove a marked edge, we get either a map with L plus 1 or two maps. And the total number of sides will be, let's say, L prime and L plus 1 minus L prime. Sorry. No, L minus 1 minus L prime. Okay. And this is a bijective construction. It means that given a map like that, you can always glue a triangle there to construct a map with one more edge, or given a pair of maps, you can glue them together here to get a new map. So it's a bijective construction. So we have an equality of those of the number of maps, And we can write TL0 equals, so T3 TL plus 1, 0. Plus, in fact, you could do the same thing with quadrangles. You would get TL plus 2, 0, plus T5 TL plus 3, 0, and so on. Plus sum over L prime of T L prime 0, T L minus L prime minus 1, 0, L prime equals 0 to L minus 1. So this is the recursion equation. This is called Tutt's equation. So which goes back to the 60s. And so Tutt wrote that equation, but not only, he solved the equation also. So one thing which is convenient is to, so we are going to reconstruct the function I was writing before with a weight per edge on the side. So we're going to take 1 over x to the L plus 2 and sum over L of this equation. And what shall we get? So what we're going to get is that, so that will give, sorry, let me rewrite the equation. And let me shift L by 1 in the equation here. So we get TL plus 1, 0, minus sum of T, J, TL plus J minus 1. Sorry, T L plus J minus 1, 0 equals sum of T L prime 0, T L minus L prime 0. I must have made a mistake here. Sorry. Okay. I'm not sure about this minus 1 here. Excuse me, I'm tired. I didn't sleep in the plane. I'm not sure about this minus 1 here. But so let's multiply by x to the L plus 2. So yes. So let's multiply this. Sorry?
Minus 2? Because you count this h twice.
No, but no, I think it's okay because here we'll get, so here we'll get x to the, so here let's multiply everything by 1 over x to the L plus 2. So here we'll get T L plus 2, x L plus 2. Here x L plus J minus 1. Sorry, let's write it this way, and times x to the J plus 1 plus 2. No, sorry. I want to multiply by x to the L plus 1. Okay. No, I want x to the J minus 1. And here. Okay, so no, I should multiply everything by x to the L plus 1, sorry. And then I think there was a minus 1 there. So L prime plus 1, x to the L minus L prime. So minus 1 plus 1 somehow. I think that's now it's correct. So it was probably minus 2 here. Okay. Okay, and remember that what I call W10 of x, W10 was the sum of TL0 x to the L plus 1. Okay, so here let me write it this way.
Can you use another pen?
Right. Okay, so what you get in the end is x minus sum over j equals 3 to d of tj x to the j minus 1 w1 0 equals w1 0 to a square. Well, this is not completely true because here in that sum you only have terms where L is positive. And sorry, you only, yes, no, sorry. You should have, if you want to reconstruct W1 0, you should have all the powers starting from 0 here. And here in that sum, since you have this plus j, in fact, you are missing some terms to do this W1 0. You miss a few terms. So let's say the terms you miss, let's call it P1 0. And P1 0 is sum over j, sum over, let's say, k, tj, x to the k, t0, sorry, what is it? J minus 1 minus k, I think. So k equals, so j equals, let me call it d to 2 to d, k equals 0 to j minus 1, so it's a finite sum. And for this purpose, let me define, so you see that this term x, you could interpret it as defining a t2. T2 equals minus 1. So here I include also t2. So this is a polynomial in x. Of degree at most d minus 1. Let me define also v prime of x equals x minus sum over j equals 3 to d of tj x to the g minus 1. So this is the definition. And so we now have an equation which is quadratic in W1 0. So W1, so v prime of x, W1 0 of x. Let me assume implicitly the dependence in T3, T4, and so on. I will always consider only the dependence in x everywhere, minus P1 0 of x equals W1 0 of x to a square. So this is again Tutt's equation. So it's just a rewriting of Tutt's equation in terms of generating series. The advantage now is that in W1 0, this is a quadratic equation, so it's very easy to solve. W1 0 of x is 1/2 of v prime of x minus square root of v prime of x to the square minus 4 P1 0 of x. Well, all right, v prime of x, so it's completely explicit. The tj's are given, so v prime of x is a given function. So v prime of x is something which we know, but P1 0 of x, it's this polynomial of x, we know its degree, but and in fact we know its leading coefficients, but some of the coefficients depend themselves on the TL zeros. with limited values of L, but which we don't know yet. So, I mean, this is not completely solved yet. There is just a few coefficients which we still need to determine. And how can we determine them? Well, we know that, so we know that everything which we have defined so far is a formal power series of T, of the parameters T1, T, T2, T3, T4, and so on. And so we want a solution of that, which is a formal series of T. And in fact, this really determines what P10 should be. I will not do it in detail, but there is a lemma. It's called, the combinatorists call it Brown's lemma. The physicists call it the one-cut assumption. But it's not an assumption. I mean, the physicists call it this way, but this is not an assumption. It can be derived. And which says that v prime of x to the square minus 4p10 of x must have exactly two simple zeros, and all the other zeros are double zeros. So it's of the form x minus a, x minus b, and let's say q of x to the square. It must be of that form. Sorry, I hope you can read. So, and this is an extremely strong constraint. In fact, this determines P10. I mean, given knowing the degree of P10, this completely determines P10. You can check. You can just, you can just write the number of equations and the number of unknown coefficients. So basically, the coefficients of P10 are unknown. A is unknown, B is unknown, and the coefficients of Q are unknown. So you have a certain number of unknown coefficients. And this is a polynomial of degree 2D. 2D minus, the degree of v prime is d minus 1. So it's 2D minus 2. And you just count the number of equations, and it matches the number of coefficients of unknown coefficients. So this determines everything. But in fact, so this is how Tutt used to do. And Brown used to do in the 60s. They solve this equation, more or less, and they replace, and they get this function. In fact, we will use a shortcut, which apparently Tutt didn't know, but which is much more efficient. So another way to state this theorem is that, so you see here we have an algebraic, this is an algebraic function. It satisfies an algebraic equation. And saying that there is only one cut, so that there is only one pair, so the square root has exactly one branch cut. This does not, the square root of q squared has no branch cut, but only AB is a branch cut. So there is only one branch cut. This means that the algebraic curve determined by this algebraic equation is of genus 0. And so this is very geometric. So another way of saying that is that the curve is of genus 0. So if a curve is of genus 0, it means that it's conformally equivalent to the Riemann sphere. So there should be a conformal reparametrization of this equation in terms of a Riemann sphere, that is in terms of a complex plane, of a complex variable. Only with rational functions. And in fact, this can be done very explicitly. So change of variable. So in fact, we shall write x equals a plus b over 2 plus a minus b over 4 z plus 1 over z. So instead of working with the variable x, we shall work with the variable z. And what is the advantage of doing that? It is that square root of x minus a x minus b is a rational function of z. It's a minus b over 4, z minus 1 over z. So you see here this polynomial. So the square root of this polynomial will involve this square root here, which is a rational function of z. Q of x is a polynomial of x, and x is a rational function of z. So everything is now a rational. So the square root of this is a rational function of z. And the prime of x is also a rational function of z. So basically we find that W10 is now a rational function of z. So with this parameterization, we have that v prime of x. So let me call that x of z. V prime of x of z. So it's a rational function of, in fact, of z plus 1 over z. So let me write it this way: sum of uk zk plus z minus k, because it's symmetric when you change k, z to 1 over z, because x is symmetric when you change z. So k equals 0 to d minus 1. And square root of x of z minus a, square root of this polynomial. So square root of this polynomial, v prime of x of z to the square minus 4p10 of x of z. This one is now anti-symmetric. Let's call it vk zk minus z minus k. Because of the square root, because of this z minus 1 over z, this one changes sign when you change z to 1 over z. And so we find that W10 is the sum of both terms. So W10 is the sum over k. So 1/2 of uk plus vk, uk minus vk zk plus sum over k, 1/2 of uk plus vk z minus k. Right? But now if you come back to the initial definition of W10, remember that W10 was sum over something with x to the L plus 1. In fact, W10 can have only negative powers of x. So this means that when x is very large, W10 should behave as, W10 should behave like 1 over, the actual definition was t over x when x goes to infinity. At least you see, W10 is a multi-valued function. So there is one branch of the square root where the 2v prime somehow compensate, or the positive powers of x exactly cancel. But if you choose the other sign of the square root, of course, they will not compensate. I mean, it cannot behave like that in both, for both determination of the square root. So we say that there is one determination of the square root where W10 behaves like that at infinity. And when x is very large, let's say that the determination we are interested in corresponds to z very large. So this means that this should behave at large when z goes to infinity. This should behave like t to the a minus b over 4 z plus O of 1 over z square. And again, that will determine everything, because you see, we want all the positive powers of z to cancel. So that will imply uk equals vk. And then we are left with only the negative powers of z. So let me now show you an example. And what time should I finish?
5:30.
Okay. Okay. So I have. Okay. So I will do an example explicitly because I think it's quite abstract. So what we find is that we must have, well, this implies that UK equals VK. And the coefficient of 1 over Z is, you see that U1 plus V1, so it's the same. U1 must be T over A minus B over 4. So 4T over A minus B. And in fact, we see that there was no V0. V0 was vanishing. So U0 must also be 0. And W1, 0 in this variable will be sum of UK Z minus K. And I remind you that the UKs were defined such that V prime equals sum of UK ZK plus Z minus K. So let me illustrate this. So I know this is quite abstract. So example. And let me do the case of quadrangulations instead of triangulations. So if we want quadrangulations, it means that we want to have only quadrangles, so only T4. T4 different from 0, but all the T3, T5, and so on are 0. So we give a weight 0 per triangle, a weight 0 per, we give a weight 0 to everything which is not a quadrangle. So we have only quadrangles. So this means the definition of V prime, so I erase this, so V prime of X was X minus T4 X cube. This was my definition. So for short, let me write alpha equals A plus B over 2 and gamma equals A minus B over 4. So for short. So notation. So now we want to choose X equals alpha plus gamma Z plus 1 over Z. So we replace this here. So this will be alpha plus gamma Z plus 1 over Z minus T4. So alpha cube plus 3 alpha square gamma Z plus 1 over Z plus 3 alpha gamma square Z square plus 2 plus Z minus 2 plus gamma cube Z cube plus 3Z plus 3Z minus 1 plus Z minus cube. Right? So now what is the coefficient of Z to the power 0? We just look. So U0 is the coefficient of Z to the power 0 in this expression. So this is alpha minus T4 alpha cube plus 6 alpha gamma square. And this should be 0. And the coefficient of U1. So U1 is the coefficient of Z in this expression. So gamma minus T4. So 3 alpha square gamma plus 3 gamma cube. And this should be gamma T over gamma. So you see now we have two equations and we have two unknowns because for the moment A and B are unknown, so alpha and gamma are unknown, but we have two equations, two unknown, so we're going to solve. Clearly the first equation is solved by alpha equals 0. And in fact, from the definitions from the beginning, we know that everything should be a power series of T4, T, and so on. And well, this equation in alpha is a cubic equation. It could have other solution than alpha equals 0, but the only solution which is a power series is indeed alpha equals 0. The other solutions will contain negative or fractional powers of T4. So, so you don't want negative powers of T4 in the solution at small T4. So the only possibility is that alpha equals 0. And for gamma square, then we will get an equation which is quadratic. Yes, quadratic in gamma square. We'll get gamma square minus T4 minus 3T4 gamma 4 equals T. And so the solution for quadrangulations is that alpha equals 0, gamma square equals 1 over 6T4, 1 minus square root of 1 minus 12T4. You can check that this is solution of that equation. And now we have, and you can check that W10 was, so T over gamma Z minus T4 gamma cube over Z cube. So this is the answer. So for quadrangulations we have computed W10. So the goal. So we have reached our goal, which was to compute this generating series. Here it is a rational function of this variable Z, and so let me remind you that X was gamma Z plus 1 over Z because alpha is 0. So this is what we get for quadrangulation. So if now you solve Z as a function of X, you will get some square roots. You can put that back into W10. So W10, you can express it directly in terms of X. It will contain some square roots. But it's much nicer written as a rational function. I don't know. I mean, it's a matter of taste. But all computations are much easier to do with rational functions than square roots. So I will soon arrive to some integrable system now. So this is the example for quadrangulations. Now let me show you how useful it is to have such an expression for this W10. Remember that W10 was the sum over all maps of T to the number of vertices, T4 to the number of quadrangles. And X to the L plus 1, where L was the size of the marked face. So imagine you want to compute a situation where you have a given size of a marked face. So remember you have something like that. And now we have only quadrangles. And so on. This is our marked face. And let's say it has size L, and all the others have size 4. So how do we get the coefficient? So if we want to count the number of maps which have a marked face of size L, we just pick the coefficient of 1 over X to the L plus 1 in this expression. So it means we want to compute the residue of X to the L W10 of X. And this is in the large X expansion, which we take the coefficient. It's when X goes to infinity. In fact, you probably know that a residue is in fact an integral. It's a contour integral. So it's better to write the measure. And when you compute residues. And the reason is that we are going to make a change of variable. We are going to change the variable X to the variable Z. And if we forget to write the measure, we may forget the Jacobian. So it's very important. So this is the residue also when z goes to infinity of x of z to the L. So and this expression, so this was W10 of x of z, but let me call it omega of z. Omega of z, and here don't forget x prime of z dz. So you see algebraic geometry is starting to come into the game. In fact, this means that the true, the really important object is not really omega of z, it's omega of z times x prime of z dz, so it's W10 times dx, it's a differential form. So in fact, our generating function is not really a function, it's a differential form. And we see that when we change variable, it changes like a differential form, not like a function. So, and also you see why I put L plus 1 here. It's because I want to have, because the residue is the term with 1 over x. And so otherwise I should put x to the L minus 1 here. So it's just more convenient. So now we have an explicit rational function here, completely explicit. X of z is very explicit. When you put it to the power L, you just take the binomial coefficient. So you just have a binomial coefficient. This is completely explicit. So this can be completed very, very explicitly. And let me give you the answer. And in fact, it will be non-zero only if L is even. So let me call that 2L. All the odd ones will give 0. I mean, so basically, if you make a map with only quadrangles, you have necessarily an odd, an even number of edges. Well, okay. I let you do the computation. So what you will find, so let me call, so I remind you I call this coefficient T2L0. So T2L0 is, you can compute it explicitly, it's gamma to the 2L factorial over L factorial, L plus 2 factorial, 2L plus 2 T minus L gamma square. So you see this is really explicit. And now you can even expand it into powers of t and t4. If you really want to compute the number of maps with a given number of vertices and a given number of quadrangles, this can be further expanded. This is sum over, so 2L factorial over L factorial, L plus 2 factorial, T to the L plus 1, sum over N, 3T4 to the N minus 1, 2N plus L minus 3 factorial over L plus N factorial, N minus 1 factorial. Well, this is just to show you that this gives a very efficient method to really compute the number of maps extremely explicitly. This formula was already obtained by Tutt, but not using this rational parameterization, directly using the square roots. But I mean, the asymptotic expansion of square roots is not too complicated, so you get that. So this is for the number of quadrangulations. So somehow you see that we can interpret this coefficient. So the coefficient with a given n. So you see n minus 1 is the power of t4. N minus 1 is the power of t4. So the number of quadrangles is this expression when you replace n by n plus 1. So we have So we have the weight, so the probability of a configuration with a given number of quadrangles on a given perimeter of a marked face. We have the explicit probability law. So we can compute expectation values. We can compute just the full probability law, and it's very easy to take the limit of large n and see what is the resulting, what is the limit of this probability law, let's say for the perimeter as a function of the number of quadrangles. Well, the number of quadrangles, you can think somehow this is the area of the surface. And so somehow you have a law which gives the area of the, or let's say the perimeter of a disk as a function of the area. This is close to the Hausdorff dimension. Well, this is not exactly the Hausdorff dimension. The Hausdorff dimension would be the area as a function of the diameter. Here we have the area as a function of the perimeter of a disk. But well, it's somehow, roughly speaking, it's the same idea as the Hausdorff dimension. So it allows to compute some critical dimension in the large size limit. But I will not go into that now. So how much time do we have? So the next thing I wanted to do now is to try to go to integrability. Well, I have erased, but so you see that given the weights, T3, T4, and so on, we can really compute this function W1, 0 of x of z. We have an explicit algorithm to compute it. And this algorithm can be rewritten in the form of an integrable system, a non-integrable system, which is the Toda hierarchy. It's the dispersionless limit of a Toda hierarchy. But so it's a non-integrable system, but I think I don't have time to do it now, so I will stop for now, I think.